Okay, so for part 2 of Unit 3-3 notes here, I do want to throw in this graph real quickly, and I think you guys have this on your example page. But be familiar with the graph for a terminal velocity, right? So again, terminal velocity, the maximum velocity that can be reached. We saw at the end of the last notes that that happens when my force of gravity and my drag force or my resistive force are equal and opposite, right? So that's when the terminal velocity happens. What I do want you to be comfortable with graphically is what this looks like in real life situations then is my velocity, right, decreases, it decreases, it decreases, it becomes more negative is what I mean by that, right? But if I look at the slope is leveling out because the slope represents, again, the acceleration, right? So the slope of this line is approaching 0 because the acceleration, as I get closer and closer to the terminal velocity, the acceleration obviously would be closer and closer to 0. So this line here shows what would happen in the absence of air resistance, right, which is what we know. If I take an object and I drop it, if there's no air resistance, then I know it's going to have a constant acceleration and therefore a relatively constant slope going downward. If there is air resistance, then again, the acceleration is not constant. The acceleration decreases over time. And so that's the big concept I want you to be comfortable with both graphically. So graphically, your graph should curve and it should basically have an asymptote towards that terminal velocity. And then even beyond the graph, I want you to be comfortable with over time the acceleration on an object would decrease as I get closer and closer to the terminal velocity. So the acceleration decreases as I approach the terminal velocity. Okay, so whether we're thinking graphically or not, I want you to be pretty comfortable with those key concepts. But beyond that, we're just going to get into a few examples here. Right, so this first example of part 2, really just goes back to then my drag force equation. So again, my drag force I know is 1/2 c rho, my surface area, and then velocity squared. So a skydiver, they're giving us the dimensions. We will assume that the skydiver is basically a rectangle that's falling. So these are the dimensions of my rectangular skydiver as they're falling. Okay, so maybe Peyton Manning with his forehead, if you will. But anyway, has the mass of 75 kilograms if the coefficient of drag is 1.1, so they provide us that coefficient, and the air is at standard temperature and pressure, which tells me rho, that P there is 1.2. What is the skydiver's terminal velocity? Okay, so this really picks up right where our last one left off. The terminal velocity happens when the force of gravity is equal to my drag force, right? The terminal velocity happens when my force of gravity is equal to my drag force, because at that point, if those forces are equal and opposite, then my net force is 0, and therefore I have no acceleration, right? So breaking this up and looking at what we know, well, mass times gravity would equal 1/2, again, c rho a, and then velocity squared. I know I'm looking for my terminal velocity, so I'm looking for v. I've got the mass, 75 kilograms. I've got gravity. Obviously, I've always got gravity to work with unless it's on another planet, in which case I would simply have to find it there first. I've got the 1/2. They give me the coefficient of drag, so 1.1. I know that this is 1.2, and this would usually be provided on like a table of information or in the problem itself if you needed it. So you don't have to memorize that, but you probably will once you do this question a few times. And then my area, right? My surface area, which is, again, I'm assuming it's basically a rectangle falling down. So 1.8 times 0.4, and then times v squared. So in solving for this expression, in solving for this equation here, that's what's going to give me my terminal velocity. Okay, so again, just a little bit of simple algebra, hopefully nothing too bad. When I solve for that velocity, I end up getting about 39.3 meters per second. So hopefully you get something around that ballpark too. But anyway, finding terminal velocity, again, the key concept here, the force of gravity is equal to the drag force. Anyway, not too bad. Alright, so example 3 may be a little bit trickier. This is using our other perspective. So they give me a small mass here. Notice it is in grams. I'm going to go ahead and put that in kilograms. So 0.002 kilograms. And then it's experiencing a resistive force B, which is proportional to its speed. So its resistive force there, its resistive force would be something like this, where again that resistive force, maybe I'll call that Fr, would be more or less our negative BV that we've seen before. I know that again because they're telling me it's proportional to the speed, so as the speed increases, that force is increasing as well. But anyway, the sphere reaches a terminal velocity of 5 centimeters per second. Again, notice my units here, so I'm going to go ahead and convert that to 0.05 meters per second. So they tell me the terminal velocity, and then they ask me to determine this time constant. Well, the good news is they're defining this for us. And we will actually talk about this a little bit later in the year. We'll come back to this once we know a little bit more of our calculus. So we will come back to this concept more. For now, though, I just want us to realize that the time constant is simply defined as m over b. Right? So in order to find my time constant, all I have to do is have to find my b because they gave me the mass. Right? So that's nothing too tricky. So in order to do that, I just have to take advantage of my key relationship here. Well, my key relationship is the fact that this happens, the terminal velocity happens when the force of gravity is equal and opposite to my resistive force. Or in other words, when my force of gravity plus my resistive force equals 0. So mass times gravity minus BV, when that equals 0, well, when that equals 0, then mass times gravity equals BV, right? And so I can rearrange this to solve for whatever I need to solve for. Now what I do want you to notice is rather than solve for B and then plug in the mass, we could actually do this all at once right now. I've defined this tau as m over b. Well, couldn't I just rearrange this equation as m over b? Right? If I take both sides and divide it by b, then I get mg over b equal to v. And then if I take both sides there and divide it by g, then I would get m over b equals v over g. Well, don't I know both of those measurements, right? I know my terminal velocity is 0.05, and I know my gravity, as always, is 9.8. So then that ends up giving me my ratio that I want. So tau, which is equal to m over b, equals the terminal velocity, so 0.05 over 9.8. Okay, so the only thing I want you to be comfortable with on this, and obviously it ends up being a pretty small number here, so about 0.005 if I've rounded that off a little bit. But anyway, the thing that I want you to be comfortable with here is, again, the key concept, terminal velocity, which tells me this equation right here. So the key concept of terminal velocity, which tells me that relationship and that relationship. And then taking this and solving for whatever variables they may define for us. Again, we will see this time constant pop back up later. And forgive my voice as it failed a little bit there, but we'll see this pop back up in play. But for now, this is all I want us to worry about. Okay, so example 4, again, obviously going to have to do with air resistance here. Really, the second I see terminal speed, I should be thinking air resistance, and so drag force and all that fun stuff. The biggest point I want you to be comfortable with on this example is, when do I use this equation, right? When do I use this one versus my resistive force being negative BV? Well, the answer to that is we're going to use this equation anytime they don't define a resistive force for us. So anytime I don't know otherwise, I actually am going to fall back on using this one. So a pitcher hurls a 0.154 kilogram baseball past a batter at 40.2 meters per second. Find the resistive force of the ball at that speed, and then they go on to tell me the terminal velocity is 43 meters per second. So I want to figure out, basically, I want to find what is d when it's at that speed of 40.2, right? So that's what I'm looking for. Well, in order to do that, I need to know, so d equals 1/2, right, c rho a, and then velocity squared. Obviously, they give me the velocity squared, but or they give me the velocity, which I can square, but that's about all they give me. So at first, this looks like a very intimidating problem. However, if I take advantage of what they give me here with the terminal speed, well, again, the terminal speed happens when the force of gravity is equal to the drag force, right? So the terminal speed happens when mass times gravity, both of which we know for that baseball, equals 1/2 c p, being the rho there, and then a, and my velocity squared. Well, since they give me the terminal speed, I know my mass is 0.145. I know the acceleration due to gravity, 9.8, right? And then I know my velocity over here, which is 43 for my terminal velocity. The reason that I left this gap here is because all of these measurements, all 4 of these measurements, they're all constants for the baseball, right? Again, the pressure, we actually know this rho here is 1.2 unless they tell me otherwise. The c would be constant for the shape of the baseball. And then the cross-sectional surface area, right? The baseball's surface area or cross-sectional area is not going to change. So all 4 of these are actually just one giant constant. So whatever you want to call that, I'm just going to call that whole thing x, but that's just a constant for me, and it's the only variable that I have. Right, so again, I've just defined all four of these together as x. Well, I can then solve for all four of those together. I can solve for my x, right, because I know everything else. So when I solve for all of those together, when I solve for my x here, I end up just, again, dividing both sides by 43 squared, and I get about 0.00077. Right, so obviously a very, very small number, but that's reasonable because, again, the coefficient's probably pretty small, and it's a baseball, so it's probably got a pretty small cross-sectional area in terms of meters, right? So fairly reasonable number for that to be pretty small. So this whole thing, again, just represents 1/2 C rho times the cross-sectional area, right? So now that I know that, well, I can just take that and substitute this in place to my equation over here, right? So if I want to find my resistive force, if I want to find my drag force, then I'm just finding D. Well, to find D, I know that that entire, right, all four of these together are collectively 0.007, right, 0.00077, I should say. Right, so I've got all those four measurements together. Trying to backspace here, there we go. So I've got those to work with, that whole thing being, again, just 0.00077. And then my velocity, right, I know would be 40.2 because that's what they defined in the problem for me. So to find my drag force, I just want you to be comfortable enough. You could find your drag force at any particular velocity as soon as you know your terminal velocity. So that's kind of the point of this question is, now that I know the terminal velocity, I can find the drag at any point. So when I calculate this number, I end up getting about 1.24 newtons, and it is a force, so I should try to represent the direction. So I know it would be against the ball's motion, right? So it would be against the ball's motion towards the pitcher, however you want to say it. But against the ball's motion, maybe is all I will say for that. So anyway, hopefully not too bad, but a different perspective, right? So the two key things that I want you to walk away with from this problem, right? I always use this equation unless they have defined this type of relationship for me. I always use this equation. And then finally, if I know the terminal velocity, right, and the mass and the gravity, then I can find the drag force at any particular velocity, which would be helpful if they asked me to maybe make a graph or to try to figure out a function that represented this. I could definitely do that if I just have those two measurements. So anyway, hopefully nothing too bad on this. So then a quick concept check on this one. So the terminal speed of a styrofoam ball is 15 meters per second. Suppose it's originally shot straight down with an initial speed of 30 meters per second. Well, the idea here, actually, if we think about it, if the ball is projected downwards with more than its terminal velocity, then the drag force is going to be way stronger than the force of gravity until that object slows down to its terminal velocity, right? Because the drag force, again, is proportional to the speed, and we know the terminal velocity would be when these two forces are equal. So if it's at more than its terminal velocity, the drag force is going to be higher than the force of gravity. So that does tell me, very importantly, that this object is going to slow down. So that rules A out, because A is not slowing down. Unfortunately, that piece of information alone doesn't distinguish between these others, because if I look at the rest of them, I can see that they all slow down. Now, E I can rule out, because if the terminal velocity is 15, right, then it's not going to slow down past 15. So this one here, which is 15 up here, it's not going to slow down and approach 0. So then the question is, it B, C, or D? Well, really, if you think about it, B and C are the same type of graph, right? They're linear until it reaches that terminal velocity. But if we think about my equation was D equals 1/2 that whole mess and then velocity squared. It's not a linear relationship. It's a quadratic relationship. So again, the big concept I want you to walk away with for terminal velocity should always follow a curve unless they have defined a function for us where it's maybe a linear function to work with. But if we're ever just working this on our own, the terminal velocity should always follow a curved projectile path. Right? So that's all that's happening here. My velocity is curving as it approaches the terminal velocity of -15. So hopefully this one wasn't too bad. We'll end part 2 of these notes and then hopefully wrap up most of the rest in part 3.